Hello guys, in this video I'm going to cover the concept of Parzen windows. So in my last lecture we started with the topic of non-parametric techniques. So this is one of the non-parametric technique that we are going to discuss today. So we started with histogram. We saw there was a problem with histogram. A lot of data is to be stored for histogram. So that is a problem over here. So then what we said was, let us just store the data. So we are going to store the training data over here, and then if we want, say, probability of x is equal to 4, we see a region around the particular number. So around 4 I'll take a region and see how many samples, how many data samples, training data, fall in this region. And that is going to be k upon n. N is the total number of samples upon the volume, or the region that I am taking. So that we covered in my last video. So now there is one thing that I want to tell you over here is v. So here one may ask a question that how to decide how much should be the region. So this thing is related to what we call as the Parzen windows. So what region should you take, how much should be the width of the region? So all these topics are we are going to see in the Parzen technique. So let us start. So yeah, before this I'll like to clarify one thing. So here you can see that I cannot keep the region very small. So if suppose I keep the region very small, say so let us take a, say I want to calculate p of x is equal to 6. So just, so if I am going to calculate this and I take a region very small, so I am taking this small region, so what will happen is, this is the actual probability for it, this is the true probability distribution that we saw, but then I can see there is only one sample over here. So k value is 1 upon the total number of samples upon the volume over here, so volume of this region. So you will see, you can see that this is a very bad estimate because there is only one sample. So if you put this region very small, you will get a very noise kind of thing, because say if suppose I want probability of 7, so again if suppose I take this much region, so it will again give 1 upon n by v, which is not true. For 7 I have so many samples over here. So the point is, when n tends to a large number, so when my n is large, when my number of samples are large, only then I can reduce my volume, or I can reduce my region. Because if there are a lot of samples that I am taking, and considering that all these samples will come from this distribution, this sum distribution, that is the true distribution of the probability that I'm finding, the likelihood. So then there will be a possibility that there are many samples over here, and then I can get a good estimate. So when n is large, I can reduce my volume of the region. But when say n is small, so like suppose in this case, I cannot have a very low value of v. I will have to have a little moderate kind of value of v. So with this, I guess we are okay to go with the Parzen windows. So in Parzen windows, what do we actually do is, we assume that the region Rn is a d-dimensional hypercube. So the region that we are going to see, we are assuming that this region is a d-dimensional hypercube. So for one-dimensional case, it is just a line. So this is not of that much interest. But say for a two-dimensional data, say this is a two-dimensional feature vector. So I have discussed this many times. So say x1 is the size of the sunflower and x2 is luminance. and I have a data somewhat like this. Also please remember, this is again class 1 data only. So this is the likelihood of x given sunflower. So we are just considering the only one class over here, because we just have to find the likelihood of this class, and this can be generalized over many classes. So here you can see this is a 2D plot. So what the Parzen window says is, you basically take a region that is a d-dimensional hypercube. So d-dimensional over here will be 2-dimensional, because there are 2-dimensional features. So it is a 2-dimensional cube which is a square. So 2-dimensional cube is nothing but a square. So with some hn, so hn is the size of the square. So this size is nothing but hn. So this is what we are saying. And now suppose we want to find a probability that say x1 is equal to 6 and x2 is equal to 5. So please note that now we'll have two things, because there are two variables over here. So now x1 is equal to 6 and x2 is equal to 5 is actually this point over here. But just extending this idea to the 2-dimensional, so I am going to draw a square over here, because that is what Parzen window is telling me, with the size as hn. So this thing is going to be hn, and the same thing we are going to see that see how many samples are inside the queue. So 1 2 3 4 5, see this gets outside 6. So there are 6 samples. So the k value will be 6 upon n, which is the total number of samples over here, upon the volume. So now you can see the here volume is nothing but this area that we have. So the volume will be nothing but hn squared over here. But for a d-dimensional space you can do this, because for a d-dimensional it will be a raised to d. So if it was a 3-dimensional space, so you would have an axis over here like this, and then this would have some height, and the volume will be nothing but the cube. So I am assuming that the region is a cube, and the volume is given by hn raised to d. Also please note that I am denoting this small n as a subscript. So this basically stands for the number of samples over here. So this will be useful in my further derivation. So we will see what this is. Now in order to implement this, so we will see how can we implement. So this was the visualization that we saw, the intuition. Now in order to mathematically implement this, what we are going to do, we are going to define a window. So this is what is a window. You take a window and you see how many samples are falling into it, and that will give you the value of k. You know how many samples are there, that is the n, and you know what is v, because it is just hn raised to d. So this is something that we fix prior. So this we know, it is like k means, you decide the value of k. Similarly you can decide the value of hn. So now we'll define a window. So mathematically I'm going to do this mathematically. So there is this phi u that I'm going to define. It is a window. So it is 1 when the u is less than half. Also please understand that this u is a vector. So like suppose if there is a 2-dimensional space, so this u will have two two components, u1 and u2. So for feature 1 and feature 2 similarly, yeah. And it is 0 otherwise. So you can see the nature of this window is like this. So for a 1-dimensional thing, suppose this is 1 dimension, so this is like half minus half to half. So because mod of this is yes, and this is 0, and this is a window like thing. So for two dimensional, if you see, it will become a square, where this will be minus half to plus half, and this will also be minus half to plus half. Oh, sorry, this is minus half. Yeah. So you can see we are approaching this. So we are going to use this function to get this. So now what I want to do is, so a hypercube centered at origin. So now what my actual purpose is, you tell me which probability you want. So here you can see, if suppose I wanted a probability x1 is equal to 6, x2 is equal to 5. So then I first saw which is that point. So that is the point of interest, that this point probability I want. I centered it. I'm taking a window of which this is the center, and then seeing how many samples are there in the window. So here I have defined this phi like this. Now I want x to be the center. So what is x? So x is the probability value that is going to be the input. So if suppose I want some probability of x, so that x is over here, as I did over here. So this is actually a capital X containing x1, x2. So this I wrote like this, and minus xi. So this I am calculating with respect to all these xi's. So here what I'm saying is, if xi will lie inside this. So let us take an example. So suppose this is one xi, and this is some probability. So this minus this, when I do, if that upon hn. So here you can see I had given a bound for this as minus half to plus half. So this was quite uh, ungeneralized thing. It is from minus half to plus half, but here I want hn. So this is basically a scale of hn. So if suppose there is this x minus xi upon hn, so I can take it like this. If suppose a sample is on this window, so it is say minus, so this much is the distance which is on the border of the region. So then what will happen is that this distance will be nothing but hn by 2 upon hn, which will give you half. So here you can see this criteria is fulfilled. So this is nothing but scaling it by hn, so that this half can now be localized to an hn. So like this, by this thing I can get this window. If xi is outside this, so this will definitely be greater than this. So if for a sample like this, this distance x minus xi will be large as compared to hn. So that will go out of the boundary, and it will give you the answer 0. So mathematically what we discussed a few minutes ago is done over here. Yes. So after this, you can see for all those samples which are inside the region, you will have the value of this particular function as 1, and for all those that are outside, you will have the value as 0, because I've defined the function like that. So I just sum this particular function for all the samples. So I have n samples, so I'm summing it with all the samples, and I will see that I will get the value of k, because say for this particular scenario, for this it will be 1 because it is inside. For this it will be 1 1 1 1 1. For this it will be outside, because say it is outside the box, and for this it will be outside 0 0 0 0 0 0. So all those samples that are outside, it is 0, this function, and for all those samples that are inside, the function is 1. So when I add up all of these, I will get the value of kn. So I am giving this notation kn, this is subscript n, for a purpose. So just hold your horses. I am going to cover this most probably in this video only. So we'll see this, why I am doing this. So I have just changed the notation quite. I used to have k over here and V over here, I have just given a subscript to all of these, Vn, Hn and Kn. We'll see why. Okay, and so this is what we have, Kn, because of this particular window. So I can substitute this value of Kn in my estimate. So this was my estimate, the probability estimate. I am just substituting the value of K. So you can see the when I substitute the value of K, I get something like this. Now intentionally I am putting this 1 upon Vn also inside for one purpose, and Hn I am taking it outside. Please note that Vn is not a function of n actually. So this Vn is just a notation for one particular thing. Okay, so finally we have this formula that the probability. So here also you can see I have changed the notation. This is having a small n over here. I'll talk about this in a minute. So we have now got the probability Pn of x, the distribution, is equal to 1 by n summation I is equal to 1 to n 1 by Vn into phi of this. Now you can see that this function, this can be any function. It need not be a square. I can have a region with, say, circle. I can have any arbitrary region. So this thing can actually be anything. You don't need to confine it to a square. You can have any function, but then it can just not be any function. It should have some conditions. Why? Because first of all, this region should be positive, because it is in totality calculating the probability. So this cannot be negative by any case. So here I am seeing that it is +1 or 0. So I cannot have some region which will have some -1, because then there is a chance of the probability becoming negative, which is not possible. So this function has to be greater than 0. The other important thing is that I should always ensure that this function has area is equal to 1. And you can now, what we have done over here is we have assumed a uniform distribution. So it can be viewed as like this, that I'm not the, say for this thing, the point of interest is P of x is equal to 4. Say this is the point of interest, the probability that I want, and I'm taking a region around it, and I'm giving probable to every particular sample. So because I'm weighting them as a constant. So this is what am I doing with the hypercube definite, when this is a cube. But then it is not necessary that I should give uniform probability to all of the samples. What if I have a particular region, say my point of interest is this, and my region is somewhat like this. So this makes a greater intuitive sense for those samples which are away from the center, from the point of interest. I am giving it a lesser weight, and for those points that are, say, closer to the point of interest, I am giving a greater weight. So you can see that this itself is a sort of a density, a probability density, and this can you need not have a constant kind of density. You can have a Gaussian kind of density. You can have any density over here. So this can be any probability density that we know, and so by this we can also define the volume. So this, please note that phi of u is a probability density. So what is phi of u? Phi of u is this thing. So this area should be equal to 1, this whatever you define as phi of u. But when you scale it, so now here I am scaling it. So when I scale it, you can see the area changes. So here you can see that I had scaled it with Hn. So here now this area is no longer 1. Now this area is something else. So it is important that I have to divide it by 1 by Vn. So this was in the formula that we saw, but this is a greater intuition of why am I taking this 1 by Vn inside the summation. So we are going to do something with this in my next video. So this Vn is over here. So basically what we are trying to say is that this thing will add up to Vn because this area is Vn. So we'll have to divide that with the area, and sum of all these will add up to n. So there are n terms over here, hence you'll have to take a 1 by n over here. So we'll stop the video over here. We'll see why does this actually work. We are going to see the derivations of how does this converge to the true mean when some n tends to infinity and all sorts of things. Thank you so much for watching. Thank you.